We've seen that differential equations.jl package solve a lot of different types of differential equations, from first-order ordinary differential equations to second-order ordinary differential equations to systems of differential equations. But so far, all of these equations have been simple and elegant equations that look like they should have their own social media accounts. But not all differential equations are so photogenic. In order to solve the double pendulum problem, you need to solve a system of differential equations that look like this. Can the differential equations.jl package handle this monstrosity? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 9 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the differential equations.jl package in order to solve first-order ordinary differential equations, second-order ordinary differential equations, and systems of differential equations. With that said, let's get started. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it Double Pendulum. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Just for reference, I'm going to include a few links. The first link is for the Wikipedia article on the double pendulum. Another link is for a website created by Eric Newman that contains a double pendulum simulation along with equations for a numerical solution. And one more link for a website that contains a very interesting collection of differential equations problems solved using the differential equations.jl package. The collection was created by Yingbo Ma and Chris Rackauckas. I provided links to all of these sources in the description below. Next, let's add a few packages. Now that everything's loaded, let's describe the problem that we're trying to solve. The double pendulum is a pendulum attached to another pendulum. The pendulums exist in a theoretical world where there's no friction and no energy loss. The bobs have mass, but are dimensionless, so they should be considered point masses. And yet, in this magical world, we still have gravity. The first pendulum is composed of a weightless, stiff rod of length L1, measured in meters, and a bob at the end of the rod with some mass M1 measured in kilograms. This first pendulum is attached to a fixed point in two-dimensional space, and is free to rotate 360 degrees in that two-dimensional space. The fixed point is located at point 0, 0, or the origin, on the Cartesian coordinate plane. The angle between the rod and the negative y-axis is θ1, measured in radians. A positive value means a counterclockwise or anticlockwise rotation from the negative y-axis. A negative value means a clockwise rotation from the negative y-axis. For certain conditions, this pendulum exhibits simple harmonic motion, meaning that the motion is both deterministic and periodic. This behavior is similar to the mass attached to a fixed spring that I covered in episode 707. The second pendulum is also composed of a weightless, stiff rod of length L2, measured in meters, and a bob at the end of the rod with some mass M2, measured in kilograms. The second pendulum is attached to the first bob, and is free to rotate 360 degrees in two-dimensional space around the first bob. The angle between the second rod and a downward vertical vector going through the first bob is θ2, measured in radians. A positive value means a counterclockwise or anticlockwise rotation from the downward vertical vector going through the first bob, regardless of the position of the first bob. Unlike a simple pendulum, the double pendulum's behavior is not periodic. It behaves chaotically. So the double pendulum is another example of deterministic chaos, just like the Lorentz system. Because it's deterministic, this means that the behavior is not random. So even though it looks chaotic, we should be able to calculate the position of the first bob and the second bob at any time t. But because of deterministic chaos, the trajectory of the bobs is highly sensitive to the initial conditions, meaning that a slight change to the initial conditions may launch the double pendulum onto a completely different trajectory. So the double pendulum problem is very easy to understand what we're trying to solve. Given θ1, θ2, m1, m2, L1, L2, and g for the gravitational acceleration, we're looking for the position of the first bob and the second bob at any time t after the pendulums have been released from their initial positions. In addition, we'll learn later that the double pendulum problem is actually easy to solve thanks to the differential equations.jl package. But unlike other examples that we've seen so far, trying to figure out what equations to solve is surprisingly difficult. Unfortunately, the differential equations that we need to solve are not listed in the Wikipedia article, so you need to derive these equations yourself. The derivation of these differential equations is well beyond the scope of this tutorial, so I went searching online for some equations to solve. Fortunately, I was able to find a system of differential equations for the double pendulum problem listed at the bottom of the double pendulum simulation at the myphysicslab.com website. The author goes through the entire derivation of these equations, so if you're interested, you can review it at your convenience. The double pendulum problem is a system of 4 first-order ordinary differential equations. The first 2 differential equations are for the change in the angles θ1 and θ2 over time, which are the angular velocities ω1 and ω2, or if you're in the UK, ω1 and ω2. The last 2 differential equations are for the change in the angular velocities ω1 and ω2 over time, which are the angular accelerations. The last 2 differential equations look intimidating, but if you go element by element, you'll see that it's just arithmetic and some trigonometry. The difficulty here is not in the math, but in the typing. There's a lot going on here, so it's very easy to make a typo, and it's very difficult to debug if you do make a typo. But stepping back from the equations, conceptually, it's just like the Latka-Volterra equations or the Lorentz system. The double pendulum problem is a system of first-order ordinary differential equations with 4 differential equations to solve. I'm not going to try to type in these equations using LaTeX, since it will take too long and there's a high probability that I'll make a typo, so I'll just refer you to the myphysicslab.com website. Even though the equations look scary, as far as the differential equations.jl package is concerned, it's just another system of first-order ordinary differential equations. By the way, using a single apostrophe is an alternate way of indicating a first derivative, which is known as prime notation. For example, theta 1 prime is just shorthand for the derivative of theta 1 with respect to time. Now, when it comes to defining the Julia function, that's going to take some work. For the most part, this Julia function looks like previous examples that we've seen. The unknown functions that we're interested in are the angles of the two rods, theta 1 and theta 2, measured in radians, and the respective angular velocities, omega 1 and omega 2, measured in radians per second. The parameters are the bob masses m1 and m2 measured in kilograms, the rod lengths L1 and L2 measured in meters, and the gravitational acceleration of Earth, g, measured in meters per second per second. We normally think of gravitational acceleration as a constant that only changes when we change locations, like a different planet. But we'll see later why I've chosen to call g a parameter. These next two lines are here just because they show up a lot in the last two differential equations. These are the first two differential equations. These last two equations are a challenge to type, so I'm not even going to try. There's a high probability that I'll make a typo, so rather than risk it, I'm just going to copy and paste the codes for du3 and du4, which are the equations that are calculating the angular accelerations of the two rods. Here are the source equations. You can pause the video if you're interested, so you can see that all I did was convert these LaTeX equations into Julia code. There's a link to my code in the description below. Now that we've defined the Julia function, we can assign the variables. U are the unknown functions for the angles, theta 1 and theta 2, and the angular velocities, omega 1 and omega 2. Let's go ahead and create a reset button. Now, we can set up some widgets for the initial conditions for the angles. I set up these widgets using angles in degrees, since it's easier for me to visualize degrees as opposed to radians. But all of the equations require the angles to be in radians, so let's convert them using the degree to radian function from Julia base. For the initial angular velocities, let's just set them at 0, meaning that once we set up the initial angles for the two rods, we're just going to release them without pushing them. Now that we've established the initial conditions, we need to place the values inside of a vector. Now that we have the initial conditions set up, let's move on to the parameters, or the masses of the bobs, the lengths of the rods, and the gravitational acceleration. We can set up all of the widgets for the parameters at the same time. Now that we've set up all of the parameters, we need to place the values inside of a vector. By the way, there's nothing special about these default settings. We'll be able to change these values later by using the widgets. Finally, we need to set up the variables for time. Okay, we are now ready to define the problem for the differential equations.jl package. And that's it. Other than having to enter a couple of really long equations, the actual workflow for solving this system of differential equations is identical to other examples that you've seen before. Now that we've defined the problem, we are now ready to solve it. Like other problems that we've seen, we can solve the double pendulum problem just by using the solve function. When using the solve function, you can specify which solver you want to use. The differential equations.jl package comes included with many different solvers. If you don't specify a solver, the differential equations.jl package will automatically select one for you based on the type of problem that you're trying to solve. A commonly used solver is called CIT5, named after the mathematician Charalampos Zitouras. Apologies for my pronunciation. You can find a list of all of the available solvers in the differential equations.jl package documentation. In the previous tutorials, I let the differential equations.jl package select the solver for me. But for the double pendulum problem, let's use a solver called Vern7, which is a solver named after the mathematician James H. Verner. According to the differential equations.jl documentation, the Vern7 solver is a good choice if you're looking for high accuracy. And that's it. Let's take a look at the solution. The value 1 column is for theta 1, and the value 2 column is for theta 2. As a reminder, theta 1 is the angle between the negative y-axis and the first rod measured in radians. A positive value means that the first rod is rotated counterclockwise from the negative y-axis. Similarly, theta 2 is the angle in radians between the second rod and the downward pointing vertical vector that runs through the first bob. A positive value means that the second rod is rotated counterclockwise from the downward pointing vertical vector that runs through the first bob. The value 3 column is for omega 1, and the value 4 column is for omega 2. As a reminder, omega 1 is the angular velocity measured in radians per second for theta 1, or the change in theta 1 with respect to time. A negative value means that the first rod is rotating in the clockwise direction. Similarly, omega 2 is the angular velocity measured in radians per second for theta 2, or the change in theta 2 with respect to time. A negative value means that the second rod is rotating in the clockwise direction around the first bob. Although this may be interesting, it's extremely difficult to get a sense of what's going on just by looking at these numbers. It would be helpful if we could plot these values. But the problem here is that there are no x or y coordinates listed here, just angles and angular velocities. The good news is that since we know the angles and the lengths of the rods, we can calculate the x and y coordinates by using a little trigonometry. Before we can plot the solutions, we need to convert the solution into Cartesian coordinates. I took most of this code from the collection of differential equations created by Yingbo Ma and Chris Rackauckas. I made a few modifications to their code, so we can do a few more things with it, but the essence of the code is from their collection. This code is a more clever way of doing what I was attempting to do in the last tutorial. Since the values of the solution are contained in a vector of vectors, this code will pull out the theta1 and theta2 values from the solution. The code will then apply a little trigonometry to derive the x and y coordinates for both the first bob and the second bob, and then place those x and y values inside of a tuple. This is the same trigonometry that we used to find the x and y coordinates in the projectile motion problem. Now, we can use this function to perform the conversion from polar coordinates into Cartesian coordinates, and then assign that data to the appropriate variables. Now that we've converted our data, we can set up some variables to keep track of the x and y values for both the first bob and the second bob. Okay, we are now ready to plot the solution. Let's start by simply plotting the solution to see what it looks like. It's difficult to see what's going on here, since all four values are plotted against time. I don't want to spend a lot of time on this plot, but you can view the individual plots by clicking in the legend. This blue line is the value 1 column, or theta 1. This orange line is the value 2 column, or theta 2. This green line is the value 3 column, or omega 1. And this purple line is the value 4 column, or omega 2. Let's suppress this plot and look at a phase-space plot for the first pendulum. Conveniently, we have the x1 and y1 coordinates assigned to the variable named pendulum1. So this isn't a very interesting plot. The default value for the length L1 of the first rod is 1.5 meters. So all this plot shows is a circle with a radius of 1.5 meters. As you might expect, the first rod simply rotates around the origin. Let's suppress this plot and generate a new plot for the phase space for the second pendulum. Conveniently, we have the x2 and y2 coordinates assigned to the variable named pendulum2. So you can just copy and paste the previous plotting code and make a few minor adjustments. Now this is an interesting plot. This looks like some child has scribbled randomly on this plot. So what are we looking at here? This plot shows all of the x2 and y2 coordinates for the second bob from time 0 through time 100. In other words, this plot shows the trajectory of the second bob. To say that this plot looks chaotic would be an understatement. But it's important to point out that although this looks random, it's not random. It's deterministic, so we can calculate the location of the first bob and the second bob at any time t, given the initial conditions. Let's suppress this plot so we can add some elements to help visualize the pendulums. black dot is the origin. The green dot is the first bob. And the red dot is the second bob. The black lines represent the rods of length L1 and L2. These are the positions of the pendulum at time 100. Let's set up our control panel by pulling down the widgets from above. Let's add some markdown so we can see the values of x1, y1 and x2, y2 at any time t. Finally, let's pull down our plot, then hide some of these cells. Okay, let's perform some analysis. Let's start by moving the time slider to 0. So this is the initial position for our double pendulum. Theta 1 is positive 90 degrees, and L1 is 1.5 meters, which is why the green dot, or the first bob, is located at point 1.50. As a reminder, that's 90 degrees counterclockwise from the negative y-axis. Theta 2 is positive 120 degrees, and L2 is 2 meters, which is why the red dot, or the second bob, is located somewhere above the x-axis. As a reminder, that's 120 degrees counterclockwise from the downward pointing vertical vector that runs through the first bob, or the green dot. As we move forward in time, you can see the chaotic trajectory for the red dot, or the second bob, depicted by the blue curves. Pretty wild, right? Now, one of the hallmarks of a chaotic system is that small changes to the initial condition can yield widely diverging outcomes, which is why long-term forecasting may not be possible, even if the system is deterministic. Let's make some small changes to the initial conditions to see what happens. As you can see, even a minor change to these initial angles alters the trajectories. So unless you know these initial conditions, it would be impossible for you to predict the locations of the first bob or the second bob in the long run, even though their trajectories are deterministic. Let's hit the reset button and change some of the parameters to see what happens. Let's start by changing the masses. Now let's try changing the lengths of the rods. So even the slightest change to any of these parameters will result in completely different trajectories. Now, what about gravity? Watch what happens when we change the value of the gravitational acceleration. All I did was change the gravitational acceleration by 0.0001 meters per second, and I got a completely different trajectory. Some common values for g are 9.8 or 9.81, but you can see that between 9.8 and 9.81, there are an infinite number of trajectories for the double pendulum system. This behavior is very different from the projectile motion problem, where a small change in g doesn't make a big difference in the trajectory of a projectile. But in this chaotic system, any slight change to the initial settings will result in a different solution. Now let's hit the reset button again and change a bunch of these settings. Both the Lorentz system and the double pendulum are examples of dynamical systems that exhibit behavior known as deterministic chaos. According to the Wikipedia article on the dynamical system, quote, "In mathematics, a dynamical system is a system in which a function describes the time dependence of a point in ambient space." Unquote. So basically, every example that we've looked at in this series has been an example of a dynamical system. Now the thing with dynamical systems is that normally they are deterministic and therefore predictable, and they tend to settle in some steady state in the long term. So in many cases, we're interested in what that steady state or states look like. The thing that made Lorentz's discovery so extraordinary was that he was able to compute a dynamical system that was both deterministic and chaotic, meaning that it was predictable, but the system never settled in a steady state. In addition, the long-run trajectory of this chaotic system was highly sensitive to the initial conditions. So unless the forecaster had perfect knowledge about the initial conditions, then it would be practically impossible to predict the future of this chaotic system, even though it was deterministic. The same can be said about the double pendulum. As we fall deeper and deeper into the differential equations rabbit hole, it seems like the universe just keeps getting stranger and stranger. What more will we discover in our differential equations journey? To find out, stay tuned for the next exciting episode. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.